Good evening all. So we are again in the laboratory of electrical technology, and today we will discuss about the short circuit test on the single phase transformer. So here you can see the panel board, and that panel board is suitable for understanding the connections, and near the panel board the experimental table is there. We can see all the experimental components or instruments are connected already. We will be discussing that, how it has been connected, and lab manual is there, so we will go through the lab manual and circuit diagram. So now we will do the short circuit test of the transformer. So we will follow the short circuit test circuit diagram. As the circuit diagram shows, we need to connect the transformer as shown in this figure, and all the components are shown here. So what type of instruments are required? First of all, we will see the transformer. Same transformer will be used, what has been used during our open circuit test discussed earlier, and the rating of the transformer is 1 kVA transformer power rating and 220 volt / 55 volt. So here we also see from the panel that 220 volt is the high voltage side and 55 volt is the low voltage side. Now, as a thumb rule, we will short the low voltage side. That means we will apply the power to the high voltage side, that is 220 volt side. So that power will be consumed as the full load copper loss of the transformer in this short circuit test. So short circuit test, as it has been already explained in the theoretical discussion classes, that is conducted to estimate the full load copper loss. So there are two windings, so there will be two losses, primary copper loss and secondary copper loss, and the wattmeter which will be used in this experiment will give the reading of the total copper loss, that is primary copper loss plus secondary copper loss. Here primary winding will be high voltage side winding. We will choose that winding as the primary winding because we are going to give the power from the variac or thermostat. We will be giving the power, and that's why this winding 220 volt side winding will be called as the primary winding and 55 volt winding will be called as secondary winding. So as per the short circuit test, secondary winding will be sorted directly by any wire, or we will be sorting with an ammeter, because ammeter has also very less resistance. So if we connect ammeter as shown in this figure, so we will consider that winding has been sorted. Okay, so now we will be discussing about the component or instrument. First of all, the 220 volt variac will be there, so we will get maximum 220 volt, or even we can go for the more depending on the manufacturer specifications. After that, we will use one ammeter to read the input current which will be consumed by the primary winding, that is 220 volt side winding. And after that, the wattmeter will be connected. Here you can see that M, L, CV points, which are very well known to all this time after discussing several times during the theoretical classes. So M and L will be the current coil, and MCV that will be showing the pressure coil or voltage coil. So M stands for say main, and L stands for line, C for common, and V for voltage. And after that, we will see that there is one voltmeter which is connected in parallel, as the voltmeters are connected always in parallel. So that voltmeter will be measuring the primary voltage or input voltage, that how much voltage we are giving. So we will be changing the voltage in the variac side. We will be reading that voltage continuously at the voltmeter, that is shown here. 0 to 50 volt range is a very suitable one, but any voltmeter is possible to be connected. But here we will see that the voltage required for this experimentation will be 5 to 15% of the full load voltage, that is 5 to 15% of the 220 volt side, means 220 voltage is the rated voltage. So 5 to 15% of the 220 volt will be the required voltage, minimum required voltage to send the full load current through the secondary, that is in the 55 volt side. So how to get the reading of the secondary voltage, secondary winding? Because we have already connected the ammeter, so we will get the ammeter reading and we will get the current. And as for the transformer specification, that short circuit current can be calculated from the kVA rating. So kVA rating is 1 kilovolt ampere. So definitely 1 kilovolt ampere should be divided by 55, because that side, secondary side, is the 55 voltage side. So automatically we will get 18.18 or say 2 ampere. So that type of ampere current is called as the full load secondary current. Now we will be discussing about the real experimental setup, that how all the instruments are connected. So first of all, we will start from the main supply board, which is installed on the wall of our laboratory. There will be one 3-pin plug and switch which will control the main supply, that is switching on and off, will give some power and disconnect the power. After that, thermostat will be there, and thermostat will be rated with the scale. But due to several usage or due to some manufacturing say mismatch with the rotating knob and the scale, we cannot tell that exactly whatever is shown on the scale will be going to the input side. So that's why we will be using some voltmeter. Here we will be using the panel meter, digital voltmeter or digital panel meter, which is shown here. So here you can see these 2 wires are coming, and these 2 wires are connected across this 220 volt side winding. So it will be measuring the voltage coming from this thermostat. So we will get an idea from this scale, but exact value will be displayed by this panel meter. Okay, after that we will get the ammeter connection. So we will start from the positive terminal of the variac, that is this one is considered, though we can consider this also, but here we have considered this one as positive. So we will keep in mind, and red wire is going to the input of the ammeter, and that input of the ammeter will be connected to the common point, and after that the ammeter will be connected to the 5 ampere range, because the full load primary current, so we have connected the 5 ampere range, full load primary current will be 4.5 approximately. So it will be also calculated by dividing 1000, that is 1 kVA divided by 220, because we are going to measure the current through this primary winding, which is high voltage winding, so 220 volt side winding, and total power is 1 kVA divided by, so it will be 4.8 will be suitable range. So we can see that 4.8 range is there. So let's see how much current is coming, because if we connect to a 2 ampere or 1 ampere range ammeter, then it will not be suitable for reading that, because the expected value or measurand will be little higher than that. So it is better to connect with any ammeter greater than 5 or at least 5. So we have connected to a 5 ampere, 0 to 5 ampere ammeter. Okay, so after that ammeter connection, the ammeter is going to the point M, we can see. So we will also see that the ammeter wire is coming, and this wire I will show you clearly. So this is the ammeter. So this is the ammeter wire is coming, and it is going to the point M. So this is the point M, and after that, that M is the current coil starting point. So ending point is the L, and that L will be going to the L will be going to the primary winding or 220 volt side winding, and that end point will be going back to the voltmeter point. So that it is displayed here in the circuit diagram. And now point to be noted that M and C points are not connected directly. M and C points are not connected directly for the wattmeter, so we need to sort it out. So that's why we have connected the C, means common point of the wattmeter. C is connected by one wire. So this wire is taken as a longer. We can use the short wire also, that is also possible. So M and C are sorted. And after that, the wattmeter negative point or the voltage terminal, which is connected here with this is the 150 range. We can see if we make it straight. So I think the 150 is not clearly visible due to the wire connections. Now it is visible, I think. Or yes, it is 150 volt connection is there. So green wire is connected to 150, and that 150 voltage or volt point is going to the returning path of the variac. So in this way the circuit diagram is completed. And in the secondary side, that is in the low voltage side, that is 50 volt side, 55 volt side, we will connect one ammeter as we have told. So one point from the positive terminal of the 55 volt is coming to the 30 ampere range, and the negative point of that point of the secondary coil is coming to the common point. So we can see here in the common point it's connected. So secondary side is also connected by one ammeter, and that ammeter is used to measure the secondary short circuit current as well as to make the secondary shorted, because ammeter has very less resistance, so definitely it will work as a short circuiting element, and that current will be 18.18 or 18.2 approximately current ampere will be flowing at the condition when the 5 to 15% voltage of the primary is applied. Why that 5 to 15% voltage is sufficient to send the full load current through here? Because whenever there will be lamps, there will be loads. But in the short circuit conditions, the lamps will not be there, no load will be connected, so only one small wire will be there which is very less resistance. So very less amount of induced voltage here will be sufficient to send at least full load current 18.18. Now for inducing that small amount of voltage, primary voltage also will be required very small, not the full is required. So that's why 5 to 15% of the 220 volt, that is of that winding rated value, is required to send the full load current through the secondary one. Here you can see that as the current value is high, that is 18.18 ampere, so definitely we will be seeing we have connected to a higher range, that is at the range of 30, means we will be connecting to the 30 ampere range, so that it comes under this measurement value. There are other scale is also there 15, but as the 18 is more than 15, so we will not choose that 15, otherwise we will not be able to measure the full scale deflection. Okay, so now we are going to switch on the powers. So those two plugs are the power to the dimmer stat as well as power to the panel board, so that we can utilize the digital panel meters, because digital panel meters need some power. Okay, so now we will increase the power or increase the voltage by rotating the knob of the dimmer stat. We will gradually increase and we will see how the meters, that is ammeter, voltmeters, are showing. So right now the voltage applied to the input increasing gradually, and you can see that the power is being consumed by the transformer, so power is increasing, and ammeter, the input current to the primary winding also is being measured, that is connected to the 5 ampere range, so upper scale will be considered. And in case of the secondary winding also, we are seeing that high value of current is going. So now it has reached to the 18 ampere, so it is approximately the full load current, and for that full load current the required primary voltage is 18 volt, so which is the very less value compared to the full rated value of the primary winding, that is 220 volt winding. So 18 is very less, 18 or 17, so it comes under the range whatever is mentioned in the manual. So now we will note down all the powers, amperes and secondary amperes readings, and also we will take the voltmeter reading of the primary winding, so that we can calculate all the circuit parameters as explained in the manual. So here we can see the primary voltage, so we will note down as 17 volt, primary current, that is ISC or I short circuit, so that will be found from this ammeter which is connected to the 5 ampere range, so we will take the upper scale. So it is 4.4 and then it is 4.45. It is coming approximately 4.5, but we will write 4.45. Okay. And after that, wattmeter reading. Wattmeter reading will be collected from this wattmeter, which is little bit fluctuating. So now for wattmeter reading, we need to check the multiplying factor for wattmeter, and for checking the multiplying factor we need to know at what ampere range and at what voltage range wattmeter has been connected. So here you can see that B1, E2 is sorted and B2, E1 are sorted. These knobs are for controlling the current capacity of the wattmeter, and depending on the connection which is mentioned in the nameplate of the wattmeter, we can see this connection, that is B1, E2 and B2, E1, when these are sorted, it is for the 2 ampere range. Here we can see that. And also we have already explained or mentioned that wattmeter voltage rating is connected to the 150 range. Here we can see, and for that also we can get the voltage rating. So we will see that for 2 ampere and 150 volt, the multiplying factor is 2. So whatever reading will be obtained here, the value, that wattage is required to be multiplied with 2 so that we can get the actual power consumed by the transformer at the short circuit condition. So we will write the value, that is 52 multiplied by 2. So wattmeter multiplying factor is 2, that's why reading 52 multiplied by 2. This is the total consumed power. And using those values, we will calculate all the circuit parameters as it is mentioned in the manual here. So please note the short circuit test calculation. That is, we need to calculate the RSC and we need to calculate the ZSC and XSC. So RSC, XSC and ZSC all are the equivalent circuit parameter which has been explained in the discussion classes, and we need to take the values of wattmeter and ammeter and voltmeter so that we can get the values of RSC. As it is shown, the RSC will be calculated by dividing the wattmeter reading by the square of the short circuit current, and ZSC will be obtained by dividing the voltmeter reading, that is VSC, by the short circuit current value, that is ISC. And whenever we will have the ZSC and RSC, we can calculate the XSC, that is the reactance part, equivalent reactance of the transformer at this condition. So it will be root over ZSC square minus RSC square. So root over line will be required to be more, yes. So it will be a little bit more here, yes. And after that, we need to calculate the efficiency of the transformer whenever the primary copper loss and secondary copper loss is already known, and also the transformer iron loss is known. So we can get the idea about the entire loss. So in the formula, you can see the efficiency is calculated by the standard formula, that is output by input. So output power is already mentioned here, and the copper loss and iron loss is added to the output power, and we can calculate the efficiency. So from the open circuit test, Wi, that is iron loss, is obtained as the wattmeter reading at that condition, that is open circuit condition, and for copper loss, it is the wattmeter reading in the short circuit condition of the transformer. Thank you.